Okay. Well, my name is Lucas Colabella. I'm going to present a work that is called Multiscale Design of Artificial Bones with Biomimetic Elastic Microstructures. And I'm doing this work in the MSME in the University of Créteil, Paris. And I started this work actually during my PhD in Argentina, in the group that is called INTEMA in the University of Mar del Plata. Well, the objective of this work is to find for a certain macroscopic body the microstructural material distribution that optimize the macroscopic behavior of the body according to certain. Oops, no. The pointer is this one. According to certain objective functions and restrictions. For this, in this work, we choose to use a parameterized microstructure and to optimize the geometrical parameters and the spatial orientation of the microstructure point to point in the whole macroscopic domain. The microstructures that we choose to use are the parameterized microstructures introduced by Kowalczyk. This microstructure consists in a cell that is defined by 4 geometrical parameters, 3 that define the thickness of the plates, and 1 that scales the microstructure in one direction to obtain orthotropic microstructures. By varying these parameters, we can obtain microstructures with solid volume fractions that go between 0 and 1. Before introducing these microstructures in the optimization method, we checked if these microstructures are able, I said that it's multiscale design of artificial bones. I didn't make the motivation of the work, but since we are trying to design artificial bones here, we check if these microstructures are able to reproduce the mechanical behavior of the trabecular bone. So for this, we perform the homogenization of the elastic properties of the microstructures using the asymptotic homogenization and a fast Fourier transform method that is called the polarization-based scheme. And we computed the bulk modulus and shear modulus, and we compare the void estimates of these modulus with the 2 sets of natural bones samples. We found here, we use these estimates, the void estimates that are dimensionless, because we found first that the artificial microstructures are actually stiffer when we make the homogenization of the artificial microstructures using the same constitutive material for the artificial microstructures or for bone. The artificial microstructures are actually stiffer, like 50% stiffer than actual bone. So we compare the dimensionless bulk modulus and shear modulus in order to get rid of that problem. And we found that our artificial microstructures are able to encompass 59% of the bulk modulus data, the natural data that we had, and 78% of the shear modulus. In order to make a further analysis of this biomimetism of the microstructure, we performed the decomposition of the stiffness tensor of the microstructures in its elastic symmetries. It's worth noting here that the artificial microstructures are orthotropic by definition, but the natural bone actually has a percentage of anisotropy that is, in average, 5% of the elasticity tensor is anisotropic. Nevertheless, we found that the artificial microstructures are able to reproduce the tetragonal orthorhombic symmetries of the elasticity tensor. Of the whole on the whole set of natural samples that we had, And they encompass 90% of the points that we had in the isotropic and hexagonal symmetries. Most of the samples that we are missing are in the, they have a low volume fraction, less than 10%. Well, for the optimization problem, then our objective is here to minimize the work of the external forces using as design variables the geometrical parameters and the orientation of the microstructure. In order to compute the objective function, we use a finite element model. To complete the optimization method, we use some restrictions on the microparameters that are defined for the by the geometry itself. We impose a restriction on the solid volume fraction, the global solid volume fraction of the body, the macroscopic body. For the optimization itself, we used IPOpt. IPOpt is an interior point optimizer for large-scale nonlinear problems. And this algorithm computes the solution of the problem using a sequence of barrier problems. Or finds the solution of the problem, or the solution or at least the solution that satisfies the first order optimality conditions. This algorithm also needs the computation of the sensitivity of the objective function to variation in the microparameters, and for this we used in this work the adjoint method. Actually, much faster direct method to compute the derivatives because it's all use one substitution to solve the equations. At difference with the direct method that use a large number of back substitution that is directly related with the size of the problem. We also use the filter in the microparameters in order to get rid of the checkerboard problems that are actually pretty common in optimization problems, and also to improve the manufacturability of the optimized structure that we obtain. For this, we used a distance-weighted filter in the microparameters, and we parameterized the size of the filter as a factor of the element size. We performed some preliminary tests to find to see if the filter is actually useful, and also to define this parameter. We found that with a filter size of at least 3 times the element size, we can get rid of the checkerboard problems, checkerboard patterns, and we also find better transitions between elements, between neighbor elements of the microparameters and on the orientation of the structure, which makes the body easier to manufacture. No? In order to verify the method, we use 4 benchmark problems: a simple supported block with a central vertical load, a cantilever beam, an MEB beam, and an L-shaped beam. We solved this problem with different restrictions on the global solid volume fraction. And we compared the results with the topology optimization method, just in order to have a qualitative comparison between for our method. But and we found that the solutions that we obtain are actually coherent with the ones obtained with the topology optimization, and the results are regarding the objective function are actually better than the topology optimization. That is expected because we are using an isotropic method here, and the topology optimization uses only an isotropic material. And the improvement goes around 40% and 75%. After that, we use the the method to solve a proximal femur, a model of a proximal femur subject to physiological loads corresponding to the gait of an adult human. For this, we used the standardized femur proposed by Viceconti. We performed two different meshes of the two different models with two different meshes. In one model, we let the microstructures to have any solid volume fraction in the whole domain. And in the other model, we divided the domain in two parts, one for the trabecular bone and one for the cortical bone. In order to have information about the solid fraction distribution, the solid volume fraction distribution in an actual bone, we use computed tomography of the femur of a healthy adult man. We used this method to compute the solid volume fraction of the femur. That it is around 56%, the global solid volume fraction of this femur. We also use the information that you obtain here to impose the restrictions in the models. As I said before, the first model it only has a restriction in the solid volume fraction at the global scale, at the macroscopic scale. But in the second model, we divided the domains in trabecular bone and cortical bone. And in the trabecular bone, we are imposing an upper bound on the solid volume fraction of 45%. And in the cortical bone, we imposed a lower bound of 80% for the solid volume fraction. Well, here we can see the results in order of the colors represent the solid volume fraction in the different elements of the model. Here we can see that for the model 1, we could obtain like the general pattern that we see in the actual bone with microstructures that have a high volume fraction in the diaphysis of the bone. We can see also the formation of the medullary canal here, but the canal is not perfectly centered in the bone, like we can see in the actual bone. And in the epiphysis of the bone, we can see mostly microstructures with low volume fraction. For the second model, since we imposed the two domains for the cortical bone and the trabecular bone, we have the perfect formation of the medullary canal in the diaphysis of the bone. And in the epiphysis, we have a center with trabecular bone microstructures and a layer around that of cortical bone. That is actually thicker than we can observe in the actual bone. Also, we can see that if you look at the epiphysis of the bone, we can see that we have obtained the principal compressive group that was defined by von Meyer. We can see that the microstructures that we obtain here we have the microstructures that we obtain at different points in the domain. And we can see that if we look at the microstructures that we obtain in the diaphysis of the bone, that's these three here, are actually quite similar for the two models. But if we look at the epiphysis of the bone, the two models obtain actually pretty different microstructures. Oh, sorry. Finally, if we look at the graphic of the cumulative fraction of bone volume against the volume fraction, we can see that the model 1 is actually the pattern that we obtained for the model 1 is actually closer to what we see in the actual bone. But this model overestimates the amount of microstructures with a high volume fraction. And in the model 2, we don't have microstructures in the transition because we only have two domains for the trabecular bone and the cortical bone. So this derives in a good approximation of the trabecular bone, but an overestimation of the cortical bone. Although the second model was actually good to overcome some of the limitations that the model 1 had, it was actually computationally expensive. When we look at the time that it took the model 1 took 1 hour to solve, and the second model took 100 hours, more than 100 hours to solve. And this is because when we are imposing the restrictions for the solid volume fraction, we are using one nonlinear constraint by element. So this becomes very expensive quickly. In order to solve this problem, we proposed to use here an isoparametric mapping of the in order to change the parameters of the microstructure for the natural coordinates of this hexahedron as design variables. Here what we are doing is to find an hexahedron that is actually encompass the microstructures that we want to use, that are in the solid volume fraction that we are interested to use. And well, as I said, we replace the design variables for these natural coordinates of the hexahedron. And this allows us to get rid of the nonlinear constraints and use only bone type constraints on these natural coordinates. We compare the solutions obtained for the nonlinear approach and for this isoparametric mapping that we propose using the 4 benchmark problems that I showed before. We found here that the isoparametric mapping approach performs from 20 times to 220 times faster than the nonlinear approach. Since we are, when we make this, I didn't mention that, when we make this approximation with this hexahedron, we are losing some microstructures that are actually in the bone volume fraction that we want to use. So since the design space is actually now is actually smaller than the design space for the nonlinear approach, the objective function is a little higher, but it's only between 5% and 10% higher than in the case of the nonlinear approach. Finally, we solved the problem of a hip implant. For this, we use a titanium implant prosthesis. We subject this implant to. We made a model of this implant subjected to the ASTM standard practices load cases that are suggested in this norm. We made 2 different discretizations of the model. One with a coarse mesh with 15,000 elements, and the other with we made a fine mesh with 850,000 elements. The coarse mesh was solved for the nonlinear approach and for the isoparametric mapping approach, but the fine mesh was only solved with the isoparametric mapping approach because it was too expensive to be run with the nonlinear approach. And for this model, we found that if we compare the results obtained only with the coarse mesh, we find that the compliance results are higher with the isoparametric mapping approach, but it performs between 600 and 2,000 times faster than the nonlinear approach. If we compare actually the fine mesh, the coarse mesh with the nonlinear approach and the fine mesh with the isoparametric mapping, we still have nevertheless we have like 50 times more elements for the isoparametric mapping. It still performs better regarding the time, the computation time. And the results in the compliance are actually quite similar. As a conclusion, We can say that we have introduced a method for the multiscale design of minimal compliance elastic solids with the biomimetic trabecular microstructures. We used this method. We verified this method in 4 benchmark problems. We also performed the computation of the proximal end of the femur subjected to physiological laws. We introduced an efficiency strategy to replace nonlinear constraints by bound constraints. Achieving a good reduction of time in the model. Well, that's all. Thank you for your attention.